Okay, objective 3, we were looking at graphing radical functions. We also threw in some review concepts here, but before we get to those, let's take a look at the new piece, which is that graph. We do have two parent graphs we want to make sure we are familiar with. The first one is y equals the square root of x. Y equals the square root of x generates a graph like this one. This graph does have a restricted domain and range of positive domain and range because, again, we can't plug in negative numbers under a square root, for example. That would generate an imaginary number, which I can't graph, so that's why we're sitting here in the first quadrant. Versus our second parent graph, which is a cube root of x, which generates a function like this one. Now, cube root of x can be negative. I can plug a -1 in here and I get -1. So we have negative range and negative domain, which allows us to kind of get this little swoopy curve look. Okay, now these functions can be shifted. So initially both of these functions do pass through the origin. And being shifted to y minus k and x minus h, we've taken our origin and shifted it to the point hk. Remembering that h is whatever zeroes out the x piece and k is whatever zeroes out the y piece. Excuse me, sorry. Okay, so demonstrating this. I'm going to do the first one, and then my recommendation is going to be that you pause the video, give the second one a shot on your own, just to kind of see how you're doing with it. So graphing the function, the first thing we would want to do is turn it into this descriptive form, this y minus k piece. And so subtracting the 1 over, we'd have y minus 1 equals root x. Now that it's in its descriptive form, we can pull out our hk, our shifted origin here. So the first question is, what makes the x part equal 0? The x part equals 0 when x is 0. And what makes the y part equal 0 for my k? The y would be 1. And so that's the starting point of my function here at 0, 1. Whoops, that's 1, 1. Sorry, 1 second. 0, 1, which is right here. Okay. And then to get 2 additional points at least, you would be plugging in. So you could plug in whatever numbers you want. My recommendation, though, because this is a square root, look for perfect squares. Because then if I plug in a perfect square under this square root, or I would get good numbers to plot, or I should say nice numbers to plot. And so what would be a nice number to square root? Well, 1, for example, is a nice number to square root. So the question is, what would x need to be so that I had root 1? Well, to get root 1, x would be 1. So plugging in 1, we get root 1, which is 1, plus 1, which means y is 2. What's another nice square number? Well, a nice square number would be 4. So what would x need to be so I had 4 under here? Well, x would need to be 4. So we have, plugging that in, root 4, which is 2, plus 1, which is 3. And so there's my second point. 2, 3, 4. And you can keep plugging in for as many as you would like, but these 3 points give us a nice little sketch here. So we kind of know where we're headed with this little curved square root function. Okay. Bringing back some review pieces. Domain, remember our x values. So as I look at this function, what x's do I touch? Well, I start at x equals 0, and there is a point there, so that would be a bracket. And I keep going out to infinity, and remember, infinity is always a parenthesis. Range are my y values, so what y values do I touch? The smallest y I touch is 1, and there is a point there, so that's a bracket, and then my graph goes up to infinity, which is always a parenthesis. Okay, so go ahead and pause the video, give number 2 a shot, restart it when you either have an answer or are stuck. Okay, so here we go. Descriptive form, this is already in descriptive form, so the next step, find my hk. H, what would make the x piece equal 0? The x piece would equal 0 when x is -2. K, what would make the y equal 0? The y would equal 0 at 0. And so that's my starting point, -2, 0. For 2 other points, you can, technically speaking, again, plug in whatever numbers you want. But like I said in example 1, I tend to recommend looking for kind of nice square numbers. And so in this case, what would be a nice square number? A nice square number would be like root 1. So the question would be, well, what would x need to be so that I had root 1? X would need to be negative 1. Because now when I plug in negative 1, get negative 1 plus 2, which is 1. Root 1 is 1 times the negative is negative 1. And another nice square root would be 4. So what would x need to be? So I had root 4. X would need to be 2. 2 plus 2 is 4. Root 4 is 2 times the negative is negative 2. And again, you could keep plugging in if you wanted to. Like for example, we could plug in 7. If you plugged in 7, you'd have root 9, which is 3, and a negative. Which will be out here, 3, 4, 5, 6, 7. So actually that takes us to the edge of our graph. You could still keep plotting if you wanted to, trying to get, say, root 16, root 25, root 36. All of those would give you nice little points to plot for your sketch. Domain, what x's do I touch? I start at negative 2, and there is a point there, so that's a bracket. And I head out to infinity. Range, my lowest y is negative infinity, and my highest y is 0, which there is a point there, so there's a bracket. Okay. Okay, number 3. I will walk through kind of all the review pieces as well on the video, but my recommendation still is to pause the video, get as far as you can, see if you can graph it, see how much of the domain, range, x and y intercepts, and rate of change that you can remember how to do, and then restart the video either when you're stuck or have an answer, whatever the case may be, but pause the video, see how far you can get. Okay? So here we go. Number 3, we have descriptive form. Adding this 4 over would be y plus 4 equals 2 times root x plus 1. Okay, so now that we're in descriptive form, we can pull out our HK. Our HK in this case would be negative 1 for the x and negative 4 for the y. So what makes those pieces equal 0? And then 2 other points, again, you can plug in whatever you want. My recommendation would be to plug in 0 and 3. Because in plugging in 0 and 3, you will generate nice square numbers underneath that radical. If I plug in 0, I get root 1. So let me plug in 0 over here. I get root 1, which is 1, times 2, so 2, minus 4, which is negative 2. And plugging in 3, I get root 4, 2, times 2, which is 4, minus 4, which is 0. The only other one you might plug in would be maybe 8. That does put you a little bit off the graph, but you could plug in 8 if you wanted to. Plugging in 8 would generate 2 for your y value. If you felt like you wanted that kind of 4th point on there to provide just a little bit more structure to your graph. And we've got our curve. Okay. Domain are my x values. So domain in this case, smallest x I hit is negative 1, biggest x is infinity. Range, smallest y that we hit is negative 4, largest is infinity. X-intercepts. X-intercept, remember, is when y equals 0. So I'm going to be putting 0 into my y spot here. 0 equals 2 root x plus 1 minus 4. So then solving, adding the 4 over, and dividing by 2, we get 2 equals the square root of x plus 1. To get rid of a square root, you square both sides. And subtracting 1, you get that x would be 3 for your x-intercept, which is confirmed by my graph. I see that I touched the x-axis at 3. Okay, so x-intercept, 3, 0. My y-intercept is when x equals 0. So we're going to go ahead and plug 0 into our x here. 2 root 0 plus 1 minus 4, which is 2 times 1 minus 4, or negative 2. And so my y-intercept would be negative 2, which is again confirmed by looking at my graph. So back from, I believe, originally unit 1, but it's been in our notes several times. X-intercept is when y equals 0, y-intercept is when x equals 0. Okay, and then last one, average rate of change. Now this one goes all the way back to kind of our Math 1 / Honors Math 8 days. Average rate of change is the same thing as what? Let's see if you can remember. Average rate of change is the same thing as slope, or I guess I shouldn't say it's the same thing, I'm sorry. It is linked to slope. And so we have an equation for slope that we've been using for a number of years now, which is y2 minus y1 over x2 minus x1. And that's how we found slope back in our Math 1 Honors Math 8 days. Now obviously this is not a line, so we don't actually have slope. We have what's called average rate of change, and for average rate of change we do f of b minus f of a over b minus a, where 0 is your a and 8 is your b. Okay? Which is very similar. It's essentially the same thing. y2 minus y1 over x2 minus x1. My x's are 0 and 8. My y's are whatever the y's of 0 and 8 are. And you could still see it as kind of slope on your graph here, right? If I was connecting x equals 0 here to x equals 8 here, this function has a rise of 4 and a run of 8. If I were to make that a line, well, a rise of 4 over a run of 8, 4 over 8 is 1/2, and that's a positive or an increasing function, so positive slope. So it still connects to that slope idea. Our average rate of change is going to be 1/2, rise of 4, run of 8. And that's further confirmed by looking here, which is what's the y value of my 8? Well, the y value of my 8 was 2. And what's the y value of my 0? The y value of my 0 was negative 2. Over 8 minus 0, which are my two x's, b and a, which is 2 minus negative 2, 4 over 8, which is 1/2. Which again, you can see by doing rise over run between these 2 points on your graph. Okay. Okay, turning the page. Number 4. Now I did modify number 4 slightly if you were following along on the notes that you guys had this year. So we would have changed this root x plus 4 to cube root x plus 4. So if you could go ahead and do that if you haven't already. And then go ahead and pause the video, give this one a shot, see how far you can get, and restart it when you are ready. Okay, turning this one into descriptive form, I need to subtract the 3 over. So we have y minus 3 equals negative 2 cube root of x plus 4. Okay, HK, my h in this case, what would zero out the x would be negative 4. Y would be positive 3. 4, 1, 2, 3. So there's my starting point. And then initial point, or additional points, you're looking for nice numbers to plug in. The nice thing about a cube root is, like we talked about at the very beginning, cube roots don't have restricted domains, so I can do negative numbers as well. And so what's a nice number to take the cube root of? Well, a nice number to take the cube root of would be, say, 1. And so the question would be, well, what does x need to be so that I get 1 under here? X would need to be negative 3. So now when I plug in negative 3, I get negative 3 plus 4, which is 1. Cube root is 1. Times 2 is 2. And 3 minus 2 is 1. What's another nice number? Well, another nice number to cube root is negative 1. So the question would be, well, what would make this inside equal negative 1? That would be negative 5. I plug negative 5 in. I get negative 5 plus 4, which is negative 1. Cube root of negative 1 is negative 1. Times negative 2 is positive 2. And so 3 plus 2 is 5. And then one more just for good measure. Another good cube root is 8. So the question would be, well, what would x need to be? So I have 8 under here. X would need to be 4. Okay, plugging in 4, we have the cube root of 8, which is 2. Times 2 is 4. 3 minus 4 is negative 1. So we kind of got one more point on our graph here, just to add a little bit more structure to our cube root. So we see a function kind of sort of like this one, which looks like, again, the cube root function. Now it's obviously been reflected over the y-axis. The reason why, for the record, is because we've got our negative multiplier there. And actually, I'm sorry, this is reflected over the x-axis because of the negative multiplier. It does also kind of look like it's reflected over the y-axis, but okay. So x-intercepts and, oh, I'm sorry, domain and range. Go ahead and take a moment, find your domain and range. Okay, domain in this case, all my x values. So in this case, I touch all my x values, so it'd be negative infinity to infinity. Range are my y values. I touch all my y values. Okay, x-intercept is when y equals 0. So let's go ahead and put 0 into our y here. 0 equals 3 minus 2 times the cube root of x plus 4. Okay, subtracting the 3 over, we get negative 3 equals negative 2 cube root of x plus 4. Dividing the negative 2, and we get 3 halves equals cube root of x plus 4. And cubing both sides to get rid of that cube root, we get 27/8 equals x plus 4. Final step, subtracting the 4, which is the same thing as subtracting 32/8. We'd get negative 5/8 for our x-intercept, which is why our graph doesn't really cross at a place that is, I would say, a very nice place to cross. Well, or at least I should say it doesn't look like it crosses at a very nice place to cross, because in this case our x-intercept would be at negative 5/8. Okay. Y-intercept is when x equals 0. So plugging 0 into my x here, we have y equals 3 minus 2 times the cube root of 0 plus 4, which does not simplify very far. Okay, cube root of 4 is cube root of 4. So actually my y-intercept is that, which definitely does not look like a very nice point on our graph there. Okay. Okay, open intervals. So find the open intervals on which the function is decreasing. So take a look at your graph. Where is your graph going down? Okay, well, our graph is going down the entire time. So where is my function decreasing? The whole thing. Remember that we always read our graph from left to right, like we talked about back in unit 1 or 2. I don't remember which one exactly. But since we read our graph from left to right, this is going down the entire time. And then D, the open interval where f is positive. So for a function to be positive, that would mean it would exist above the x-axis. So if you wanted to write that, f positive above the x-axis. So the question is, where am I above the x-axis? I'm above the x-axis from negative infinity all the way to where I crossed the x-axis, which I found out earlier was at negative 5/8. Okay. Okay, last one. Number 5. Go Go ahead and pause the video, oh, real quick, sorry, I did modify number 5 as well, made it 2 minus x instead of x minus 2, so go ahead and make that change. Then pause the video, give it a shot, restart it when you're ready. Okay, so turning this into descriptive form, we have y minus 1 equals 2 times root 2 minus x. Okay, my hk in this case, my h would be what zeroes out the x, which would be 2. My k would be what zeroes out the y, which would be 1. 2 additional points, so we want nice square roots, so I'd like a 1 under there. How do I get a 1? If x is 1. When x is 1, I get root 2 minus 1, or root 1, 1, times 2, 2, plus 1. 3. And then another nice one would be 4. So what could I get? How could I get the square root to be 4? X would need to be negative 2. Okay, plugging in negative 2, we have root 4, 2, times 2, 4, plus 1, 5. And so we've got our little function here. You also could plug in negative 7 if you wanted to for good measure. If we plugged in negative 7, we'd get root 9, 3, times 2, 6, plus 1, 7. And so you could plot that point as well if you wanted to. Okay, so you've got your little square root function there passing through your points. Okay, domain and range. Domain. What x's do I touch? Well, I start at negative infinity and I go to 2. Range. What y's do I touch? Well, I start at 1 and I go up to infinity. X-intercepts. Now this one's an interesting one because if you notice on your graph, we don't actually have an x-intercept. The reason for this, if you were to look at your equation, is as follows. An x-intercept is when y equals 0. So plugging in 0. If I were to solve, subtracting 1 and then dividing by 2, I get something that's actually outside of my domain and range here. I get that a radical equals a negative 1/2, which isn't possible. And we'll look at this more in the next objective, why that's not possible, but this is kind of the proof in the pudding type thing, which is the fact that we got this root equals negative 1/2 when we get to our next objective is going to tell us this is no solution, and we can see that graphically. I have no x-intercept here. Right? Y-intercept, though, that I do have. So y-intercept is when x equals 0. So we have plugging in 0 for x, 2 minus 0 plus 1. Which again, like the last one, doesn't simplify very far. This is root 2 plus 1. Or I should say 2 root 2 plus 1. And so that's my answer. Okay, average rate of change. Average rate of change between negative 7 and 1. So again, you can kind of see it on the, you can see it on the graph between negative 7 and 1. This goes down 1, 2, 3, 4 over 1, 2, 3, 4, 5, 6, 7, 8. And it's the negative direction, so down 4 over 8 would be negative 1/2. Further confirmed by doing our f of b minus f of a over b minus a, where negative 7 and 1 are my a and my b. My y coordinate at 1 was 3. My y coordinate at negative 7 was 7 over 1 minus negative 7, which is negative 4 over 8 or negative 1/2, like what we see in our graph there. Okay, and so where is the function negative then? The function is never negative. Because my function is never below the x-axis. Below the x-axis. Okay. And so that's objective 3, which is graphing with some review stuff. And there you go.